Hello. We are going to discuss the estimator for the quantile regression model. And as you know, we are minimizing the sum of check functions, which is the loss function, which replaces the square function, the quadratic function. And we will denote this as a criterion function Q and hat. Then in theory, in the population world, if you have an infinite number of observations, we learned that the true parameter will minimize this problem. And the first order condition can be written in this way, which is also considered parallel, same as the theoretical part. Here, let me discuss a few computational problems first. So first, look at this. The first order condition, basically, we are solving this problem. This is the main problem in our computation. And 0, we are solving something equal to 0, but the function is a indicator function. So it is 0 and then jump 1. It goes 0 up to up to a certain point, and then jumps and then becomes 1. So because it is summed, there are a lot of jumps, it's like step. It's like staircases. So that means there are a lot of flat areas. That means the second derivative of this first order condition, the second derivative of the criterion function is 0 almost everywhere because it's flat. It's stair like this. So it causes a big problem. Many of optimization problems, numerical algorithms, need the second order derivative. However, here it doesn't work because second order derivative is 0. So doesn't work. And another problem here is because it is flat, it may be flat at some points. That means the solution may be any point on the flat area. So the minimum may not be unique. Then which is another problem in computation. In theory, it is not a problem because as the sample size goes to the infinity, the probability of this problem happens will converge to 0, but they are problems in the finite sample. So anyhow, I think I cannot discuss the computational problems right now. And anyhow, you are going to use some program, and the program will solve out these problems, like these problems easily. So just in case if your program does not work, then it could be one of these two reasons. There are additional maybe problems, but in general, I think these two are most fundamental problems. And before going to the asymptotic normality, I will review what we have done earlier. So first, we started from the first order condition. Suppose that we have this kind of first order condition, and then if this is differentiable everywhere, you may linearize, approximate this function to a linear function like this. So the purpose of doing this is we need this part. And we use intermediate value theta bar. And then, because we are interested in this part, rearranging the terms, we get square root n times the estimation error can be written as something inverse square root n something. And we know this part converges to normal distribution by the central limit theorem, and this part converges to constant of matrix, invariable matrix, by the uniform law of large numbers. Then we get this. This is how we proved the asymptotic normality. However, now the problem here is it does not work. This line, the Taylor theorem, does not work anymore. So we have to consider a different technique. This technique is more difficult and it's less standard because it is used only when the criterion function is not differentiable everywhere. But this problem is important in theory. So I have to teach this because in case if some of you are going to specialize in econometric theory, they need to know this. In general, I'm just sketching the proof, so if you can tell if you are good at theory or not. If you have no interest in these kind of things, think more carefully about econometric theory. Okay, we are going to assume the consistency. Consistency is not much different. Consistency is not a big problem because the main problem is the linearization. The differentiation is not possible everywhere. One point has a problem. And then now the first order condition, the function for the first order condition can be written this way. And as I said, its derivative is very weird because the derivative is 0 everywhere and it is not differentiable one point, right? So the Taylor expansion doesn't work. To avoid this problem, what we are going to do here is we will consider this. We will like so we know the first one condition is this guy equals to 0. G beta hat summation equals to 0. And we decompose this guy into several parts. First, replace beta hat with beta 0. So this will be cancelled out by this guy, and this will come into this part. So this will come into this part, and this is playing the same role as this guy, right? So in the Taylor expansion, anyhow, you are going to get this term, and we need the same term here. And of course, later you have to cancel out the match the terms. And then second term is important. We replace the the sample mean with population mean. We replace 1 over n summation with expectation. The reason why we are doing this is because after taking the mean, taking the expectation, this guy is differentiable. So this is differentiable. So here you can use the Taylor theorem here. So that is the trick we are using. So we in the previous standard case, we just use the finite sample approximation, but in finite the problem here is everything must be differentiable in the finite sample. But now we have a problem in the differentiability. So in the standard method, differentiability, the linearization is the first step, and in the second step we apply the limit theorem. We take everything goes to the infinity. So linearization first and limit second. But now we cannot do that. So instead we take the limit first, and then now it is differentiable, so we may linearize it. So the order is changed. And then we get these 3 terms. So and now you know what we are going to do for A. So we will in simply speaking, to get to the point, we are going to apply the center limit theorem for A. Exactly same as before in the standard method. And in B, we are going to use the Taylor theorem. We will linearize this, and we need to have this. So we have to extract this term by applying the Taylor theorem, which will be applied here. And the problem is, so A and B are easy to handle, quite similar to what we did, but main problem is C. we have to show that C converges to 0. It is ignorable. So C is ignorable, then our proof is complete. Showing that C goes to 0 is the main problem. That requires a very much complicated theory. Let me try. So first, the term A goes to a normal distribution by the central limit theorem, which is clear. And the variance can be written in this way. It is simple algebra, so you can study it by yourself. And what's interesting here is it takes this form. So it simplifies a lot. And here also you can read the algebra. I'm not going to read the algebra. And the B, the second term, B is now differentiable. So we can show that its derivative written in this way. So this term, it can be written as something multiplied by the estimation error. We needed this term and we got it, and the derivative is the second order derivative G, which was the same, playing the same role as before. It should be invariable, and now we do not need to worry about the uniform convergence now here, because it's already expectation, so there is no convergence. Expectation is taken when you have an infinite number of observations. So in the population, there is no convergence, there is no sample size. So there is no uniform convergence anymore. We just need this invariable. And remember, the invariability of this is the second order condition of the minimization problem in the identification part. And the C, the last term, is more complicated. So I'm going to stop here and we'll continue the last one in the next video. So thanks for watching. See you later.